I think I'm going to just solve a couple of problems because I'm going to ask similar problems in the next homework. So I think I still didn't open the homework, right? Yeah, I'm not sure about this. So if I already opened, then that means that I did. In any case, let me start with this. Okay. Just keep in mind that the capital M is different than small m. This is one of the important things. I mean, I'm using these are different symbols, all right? Just keep this in mind. So these are not the same symbol, right? So I could have called these as M1 and M2. I think I should actually use these kind of things so frequently that you just get used to the idea that if it's a small m, then you cannot use a capital M. Okay, so in any case, why do I ask this? Because there's a similar question. So that's basically for linear acceleration, but in the homework, you're going to meet a situation where the acceleration is for a uniform circular motion. But in any case, the problem is like that, okay? I'm going to solve it on purpose because there is also some kind of an issue with the Newton's third law as well. But let's just, I mean, apart from these kind of small details, it's actually quite a straightforward problem. So what we do is we just draw the free body diagram. So I'm just going to do this. Okay, so that's the big block, that's the small block. So for the small block, the gravitational force is the force acting on it. There's a normal force between the big block and the small block, and probably there's a frictional force, which is pulling it in the upward direction, because that's basically what we want. We want this to be not sliding downward. And so as a result, it remains at rest in here. So that means that there has to be an upward static friction force, okay? So these are the all forces acting on the small block. So you can see that since there is a normal force in here, if this is non-zero, then there will be an acceleration in the forward direction. On the big block, therefore, since these two forces act between these two blocks, there should be the corresponding reaction forces, right? Let me show them like that, okay? So Fs basically pushes the big block downward and pushes the big block leftward. Here, for small block, Fs pushes it upward and pushes it forward, right? These two forces are just opposite to the other, the corresponding forces. And then we have the weight of that big block. And then we have this external force. And finally, there's a force applied by the ground. So I'm going to call this as N ground, right? NGR, okay? So these are the forces. Now, in the next step, I would like to also talk about the acceleration. So basically, we are looking at a situation where both of them are accelerating, have the same acceleration, because if the blocks do not, if this small block does not accelerate down, or it just stays at rest relative to the big block, then their relative velocity is zero. That means relative acceleration is zero. So that means they both have the same acceleration in the same direction. Okay. So again, I mean, these are vectors and these are just components along these vectors. Just keep this in mind. So acceleration has the vertical component of the acceleration would be zero in that case. And the same is true for all the other forces. So again, this is straightforward. I'm just going to choose the X and the Y axes like that. So along the X direction and along the Y direction, I'm going to write down F equals ma. So let me quickly write them down. So I'll start with this. So we have N is equal to mass times acceleration in here. And then Fs minus mg is equal to 0 along the Y direction. Along the X direction, we have F minus N is equal to mass times acceleration. And along the vertical direction, N ground minus Fs minus mg, that's equal to 0. So this time I'm not explaining, right? I'm not explaining that, well, we don't subtract the forces in here, we just add them up. Or I don't say that, well, that's basically, there's mass times acceleration on that side. So you know these, all right? There's no reason to repeat them. Okay, so again, this is quite straightforward. There's nothing unusual in here, but probably you haven't seen these kind of things in that form. So therefore, this might actually appear foreign to you. I mean, probably you haven't solved a problem like that before. And for that reason, some things may actually appear strange. So for example, some people may actually just set the static friction force to be equal to mu s times n. Well, that doesn't happen in here, right? Sorry about this. In any case, we solve the problem first, and then we check, let's say, after solving, we just check whether the static friction force is indeed smaller than mu s times n or whatever, okay? Just keep this in mind. So at this point, we don't say anything about the magnitude of the static friction force. So we can find what Fs is. Fs is equal to mg, so that's one of the unknowns. Normal force and the acceleration, they are also unknown. So let's see. So ngr in here is equal to that. So I'm just going to use this equation as well. So therefore, the normal force applied by the ground is equal to the total mass times gravity. Okay, so as a result, these two equations are handled. What I'm going to do is I'm going to add these two equations, just add them up. If you add them up, yeah, let me quickly do it like that. So first equation is this, and the second equation is this. Add them up. So the normal force cancels in here. And on the right-hand side, I have a single unknown. Okay, so that means the acceleration is equal to F divided by m plus m. Okay, and then we use this equation to find the normal force. So therefore, the normal force is equal to little m divided by the total mass times F. Okay, I mean, this must be unusual for some of you because the normal force didn't appear to be mg cosine theta and things like that. But in any case, so at this point we discuss, okay, so what is this? First of all, what is this? All right, let's just go back to the main problem. So we would like to find the minimum force necessary so that the small block doesn't slide down, okay? But what we assumed in here is that somehow the force in here is sufficient for this condition to be satisfied. So therefore, the small block doesn't slide down. So it can be any force. It's not necessarily the minimum force, right? So we are assuming that F is sufficiently large so that no sliding occurs. So I impose the condition that no sliding occurs. So under that condition, so all of these variables should have these values. So that's basically the answer in here. So solution when no sliding condition is valid. So depending on the value of the force that you apply, you might have different solutions. Static friction force and the ground, normal force applied by the ground is going to be the same in all cases. But these are going to be different, the acceleration and this, the normal force, okay? Just keep this in mind. So at this point, we would like to check if this solution is physically possible. And in that case, what we do is we just check this equation. So let's then check is static friction force less than μs times n? Is it, what's the static friction force? That's mg. Is this less than μs times this little m times F divided by the total mass, right? Okay, so we would like to check this. So little m somehow cancels, but this other little m stays in here, which means that capital M divided, sorry, total mass times gravity divided by μs should be smaller than F. Okay, which means, again, this is the inequality part in here is that, I mean, F can be equal to this one in any case, which then implies that the left-hand side is basically the minimum force in here. So that's minimum force, minimum force, because this equation is essentially is an inequality. So this inequality is an inequality where F is, if F is greater than the quantity on the left-hand side, then this is satisfied. So therefore, the minimum possible value that the force can take is the left-hand side, right? That's why I call the left-hand side as the minimum force. So therefore, the minimum force is equal to the total mass times gravity divided by μs. All right, so that's the answer to the problem. Okay, I know that all of you, I mean, most of you do not solve it like this, right? You don't form inequalities. You don't form inequalities. So I know that at some point in here, so since the question is asking for the minimum force, you're going to set Fs to be equal to μs times n, right? I know that you're going to do this and insert this value in here. So that's also possible, but sometimes this might be misleading. Okay. The reason is that the conditions might be such that this is never satisfied. For example, there might be some situations. So I cannot give a very simple example of a problem like this, but in any case, it might happen, right? I think in the next problem that I'm going to solve, I'm just going to show you this one possible situation, but I'm not going to go into details. Okay. So as a result, yes, so there are a few comments that we can make in here. So first, can we also find acceleration by thinking like, yeah, we can think like this, right? So what happens is this, so both of these blocks basically act like a single block, act like a single block with mass m plus m, right? Because they have the same acceleration, they have a common acceleration. Well, they don't move relative to each other. So if they don't move relative to each other, then there's no problem. So that means there's a force applied along that direction. And there are also these forces in the vertical direction. So we have the weight force, and then we have the force applied by the ground. So from here, we can easily see that the F is equal to total mass times the acceleration. So therefore, acceleration can be found in terms of the mass like that. And so the normal force applied by the ground is equal to m plus m times g. Okay. I mean, you could have found these two results by using this kind of an argument as well. But in any case, I mean, we are doing this systematically, right? We just write down we first draw the free body diagrams of for each individual object, and then write down the equations and then solve them. So as a result, unless there's a good reason for solving, going to shortcuts like that, I suggest that you follow the usual approach, because you're going to get all the equations that you need to solve the system. And well, the number of equations will also be equal to the number of unknowns. So as a result, if you do this systematically, then there's less of a possibility of making a mistake or missing something. Okay. So just keep this in mind. But again, why it is important to keep in mind these action-reaction pairs is kind of important for getting the correct solution. And the same thing is true for the static friction force as well. Okay, any questions in here? Okay, in any case, so nothing special. All right, so I'm going to solve this problem. Should I say solve? I don't know. Because this problem has some peculiar features. There are some very special cases which kind of makes it a little bit difficult to discuss. So I don't want to spend too much time on that, okay? So it's more or less the same question, except that instead of having a vertical line in here, I mean, our angle is not 90 degrees now. So this is like this problem in here, right? Just like that problem, except that now the blocks are like these, right? They just have an interface which makes an angle with the ground, okay? So that's the only special case. I can solve the same problem like that, but I'm not going to do this. So as a result, what I'm going to do it like this. So I'm pushing it in the forward direction, but I will be just asking for the value of the acceleration. So let me do it like that. So let me also add this mu s. There's no friction in here, but who cares? There is no friction between the incline and the ground, but again, who cares? Because we're not going to include the incline into the picture. Okay, so the question is, what are the minimum and maximum values of the acceleration A the incline should have so that the block neither slides down nor slides up, right? It remains at rest relative to the incline. Okay. This is also straightforward, but there are too many equations. Okay. So the equations will be crowded, but that's also very simple. I solved this problem for the case where there is no friction. In that case, there's just the right value of acceleration. So if the acceleration has right that value, then it will stay at rest. But if the acceleration is slightly bigger, this is going to slide up. Sorry, this is going to slide up. And if it is smaller, then it's going to slide down. If there is friction in here, in that case, there's an interval for the acceleration, which means if the acceleration is below this minimum value, if the incline doesn't accelerate sufficiently, then this is going to slide down. On the other hand, if the acceleration of the incline is too large, right, it has an excessive acceleration in the forward direction, in which case this is going to move up, basically accelerate up, right? So we want to describe the intermediate situation. So in any case, how do we solve? So we suppose block does not slide, and then solve the equations accordingly. So that's what I'm going to do. All right, so that's the incline level. So that's the free body diagram. Free body diagram, okay. We have the weight force acting on the block, where that angle is theta, whatever. There's a normal force acting on the block. And then there's a friction force, and I couldn't decide if the friction force should be drawn downward or upward. Right, there are decisions that we have to make in here. Okay, so in which direction should I choose the static friction force? In any case, I would like to solve the problem for both of these situations, right? In one case, well, I mean, it should neither slide down nor slide up. So, I mean, if the acceleration is maximum, which means that if the acceleration is slightly bigger than this is going to slide up, in which case the static friction force will be pointing downward, okay? Meaning that at this point, for example, the static friction force actually has its largest possible value. So that means if I change the acceleration a little bit further, then the static conditions are going to cease, okay? And then it will start sliding in the upward direction. In any case, so one possibility is that I can solve this problem and to find the maximum acceleration, and then start the problem again, and then choose the static friction force in the upward direction, and then solve for the minimum acceleration. That's also a possibility, but that's completely unnecessary, okay? So the reason is this: when I use this notation in here, sorry, that particular notation, so when I draw an arrow and add a scalar symbol in here, that means that this Fs is the component of the force along this particular shown direction. So that means Fs can be negative, okay? So let's just note this, right? Fs is the component of the frictional force in the downward direction. Okay, so that means Fs can be positive as well as negative. Okay, so that means I can, both cases of A max and A min can be treated with this particular free body diagram. No problem with this. So, I mean, just keep this in mind, because it's going to make your life easier. So you just get used to the fact that the component of forces can be negative, okay? So you don't have to draw the free body diagram in such a way that all forces have positive components. This includes the normal forces as well, right? No problem with this. So in some cases, you are going to solve some problems where some of these forces will turn out to be negative at the end, but you just stop there and look at these values and interpret them correctly. So in any case, when we solve this problem and it turns out that Fs is negative, then we will say that, well, the the force vector is basically pushing the block upward, right? That's the correct interpretation, but we are just going to use the same free body diagram. How are we going to determine the magnitude? That's basically, I mean, this is a constraint force, right? The constraint is that this is not going to slide down the incline, which means that the acceleration is in the horizontal direction, right? That's the constraint. Once you apply the constraint, you find the static friction force. That's it. It's just like the other constraint forces, like the normal force or the tension force. When you impose a constraint, your equations give you the values of the static friction force, okay? And then after finding the solution, you then check the friction laws. All right, so that's basically what we are going to do. So we have seen this. So in this kind of problems, it's kind of easier to use this frame. But if you want, we can also use this one as well. Depending on what you obtain, what you want to get, it's kind of hard to decide. But I mean, let's just use this one. I think this is a little bit more convenient for us. Okay. Because I don't want to deal with some trigonometric identities. Okay, so let's just do it like that. So as a result, along the x direction, we have Fs plus mg times sine theta. That's equal to mass times a times cosine theta. And along the y direction, we have n minus mg cosine theta is equal to mass times the acceleration of acceleration times sine theta. Again, a is the component of the acceleration along that direction. Just keep in mind that this is the x component of the acceleration and that's the y component. Let me also leave them in here. So I'm going to assume that a is known, so I'll just compute what Fs and n are. So therefore, Fs is equal to ma cosine theta minus mg sine theta. Well, m is common, so therefore, let me just take this inside this common bracket of m. So take n out, take the mass out. So for the normal force as well, I'll do the same thing. So that's a sine theta plus g cosine theta. Okay. So that's basically the solution. So for that acceleration, provided that the block doesn't slide down, this has to be the exact value of the static friction force. This has to be the exact value of the normal force, provided that the no sliding condition applies. We would like to understand if for that given acceleration, these conditions are satisfied or not. So we basically need to check the friction laws. Okay, I need to therefore check this inequality. So this time there are two inequalities. So Fs, static friction force, has to be in an interval. Its value should be between this positive μs times n and negative μs times n. So that's the inequality that we have to be checking in here. Okay, so as a result, I'm just going to write this thing down like that. So this is a cosine theta minus g sine theta must be less than μs times a sine theta plus g cosine theta. And then on this side, we have minus μs a sine theta plus g cosine theta. Okay, so I'm just going to stop here, but in each case, you get an inequality. So for example, for this one, you're going to get like a times cosine theta plus μs times sine theta is bigger than, let's see, g times sine theta minus μs times cosine theta. This is one inequality in here. So from the other inequality in here, you get something else. I think you are going to get like a times cosine theta plus, sorry, minus mu s times sine theta is less than g times sine theta plus mu s times cosine theta. I mean, what I meant by crowded are basically these equations. So at least for symbolic solutions, these are a little bit complicated, but I mean, these are the ones that you need to solve. So example, I'm just going to give some examples. So let's say theta is equal to 53 degrees. And let's say mu s is equal to 1. And the question is, what is maximum and minimum accelerations? I mean, what's the interval of acceleration that we should have so that this block doesn't slide? Okay. So in any case, so the first equation is, first inequality is this. So I'm just going to write them down in here. Let's see. We have G. Yeah, let me write sine of 53 degrees minus mu s times cosine of 53 degrees. That should be less than cosine of 53 degrees plus mu s times sine of 53. Don't worry about this. I'm just going to insert in the numbers. So G is 10. Sine 53 degrees is 4/5. Mu s is 1, and this is like 3/5. Okay. And here, this is 3/5. This is 1, and that's 4/5. Yeah, I think I have a problem with my camera. In any case, so that's 1/5. This is 7/5. So that actually implies that A is bigger than, yeah, let me leave this as G. So I'm just going to leave this symbolically. So that's basically something that we can better understand. So if the acceleration is bigger than 1/7 of the gravitational acceleration, I mean, this is one condition that must be satisfied. So that means that this is the minimum acceleration then. What about the maximum one? In that case, I need to use this part of the inequality. And so therefore, this is the equation that we have. So I'm going to continue this one with the green color. Okay. So let me first write them down. Cosine 53 minus mu s times sine 53 is less than gravity times sine 53 plus mu s times cosine 53. So A is in here. Let's see, cosine 53 is 3/5. Mu s is 1, and sine 53 is 4/5. Sine 53 is 4/5. And mu s is again 1, so that's 3/5 again. So the right-hand side is again the same. So that's 7/5. The left-hand side is equal to minus A/5. Which then implies that I think I need to move minus 7g to the right-hand side. So therefore, this becomes greater than minus 7. But I know that this first condition is satisfied. So therefore, this doesn't give us anything new. So there's nothing new in here, which means as long as A is bigger than this one, there's no maximum acceleration. So however you push, however hard you push, it's not going to accelerate up. That basically essentially means that the angle of the incline is so large that, and the friction is so large, so frictional coefficient is also sufficiently large, so that whatever the acceleration is, it never accelerates up. Okay, so that means in that case, so let's say it like this. Minimum acceleration is 1/7g, and the maximum acceleration is infinite. Okay. So that means for any value of acceleration, bigger than 1/2 of g, the block doesn't slide. The block does not slide. All right, that's the answer then. I mean, I just solved the problem for an unusual situation. I mean, normally, if the friction coefficient is sufficiently small, I mean, μs was very large in here, so there's a very significant friction in there. If the friction coefficient is sufficiently small, you're going to find both a maximum and a minimum acceleration in here, both a maximum and a minimum. Here, we just have some kind of an unusual situation. Okay, I think we are kind of finished with today. So that essentially means something like this. I mean, think about the minimum acceleration. So this is for the minimum acceleration. In that case, this is a situation like that. The block actually is about to slide downward, but it doesn't, which means that the static friction force actually prevents it from sliding downward. And it basically has the maximum possible value. So in that case, the static friction force is equal to μs times the normal force. It basically is equal to its maximum possible value, which means if I decrease this acceleration further, in that case, to keep this block in place, I need a friction force bigger than this. That's not possible. So in that case, it will start sliding down, right? It will start sliding down. Okay, so that's for the minimum acceleration. So in that case, the static friction force is exact at that extreme point, at that limiting value, is equal to μs times n. In the other extreme, we have this situation in here. The acceleration is large. It can be as large as possible, actually. In that case, it turns out that, well, the static friction force is basically pushing the block in the downward direction. Okay. But I mean, if I increase the acceleration further, the static friction also increases further, but it never reaches to that maximum possible value. So in this situation, that static friction force is always strictly smaller than its maximum possible value, right? No matter what the acceleration is. So in this kind of a problem, for example, Fs never reaches to that maximum possible value. And as a result of that, I mean, if you solve this problem, for example, for the maximum acceleration problem, by assuming that Fs to be equal to μs times n, then you're going to get the wrong result. So let me write this as a comment in here. So note, if you solve this problem by first setting static friction force to its maximum value, then you will get a nonsensical result. Okay, I mean, this is an Amax problem. You would like to find the maximum possible acceleration. But to solve this problem, if you make this assumption at the beginning, then you're going to get something nonsensical. I suggest that you try this and see why. At the end, you are going to find the acceleration to be negative in that case. But the real physical reason is that under these conditions, just a small amount of frictional force is necessary to keep this block on the incline, no matter how large the acceleration is. And so as a result, I mean, this much friction is never becomes necessary. And so as a result, you have to solve the problem in the way that I have solved it. Okay. let me leave it like that. So that's kind of, I don't know. I mean, that was not a good problem solution, perhaps. In any case, so this is actually related to the banked rod problem. Banked rod. The mathematics of this problem is the same as this one, but the problem is different. So in that case, in highways, in autobahns, the traffic should flow very fast, right? So the cars are moving like 120 kilometers per hour. They are moving very fast. And so as a result, if a highway has to take a turn, in that case, they build the road in a banked way. So they just make it with an angle, right? So the situation is something like that. This is basically the road surface. This is the road. And the cars are moving like that. They are moving towards us. So I'm just going to draw it like that so you can understand what's going on here. They are coming towards us, but this is basically, this is the direction to the, let's say, to the center of turn, right? So, I mean, the center of turn is somewhere like that. So as a result, that's the direction of the center of, toward the center of the turn. So therefore, these cars, they don't change their speed. So therefore, they have an acceleration towards the center, right? We know that this is like v squared over r, whatever. In that case, however, you want to make sure that the cars do not slide upward and do not slide downward the road, right? You don't want these kind of sliding motion. So let's say it like this: the cars should not slide down or up. Okay. So you want that. You want to make sure that this is the case. And so somehow you just adjust the banking angle so that, I mean, whatever the typical speed that the cars should have on that highway, you just adjust this angle, right? In any case, so the physics of that problem is different than the physics of this accelerated incline problem, but the mathematics is the same. So this problem has exactly the same solution as this problem, right? It's just the physics is different. In one case, we have a uniform circular motion, so therefore the acceleration is a centripetal acceleration. In that case, this is a linear motion in one dimension, so therefore the acceleration is just the one-dimensional acceleration. But the physics of what's going on in here is going to be the same, okay? I mean, that's the main reason why I have solved this problem. I know that in textbook, you are going to meet these banked road problems. I may also ask a question about this in the homeworks as well. It's just a one common variation of these kind of problems, actually. So this one should also be treated in the same way. Okay. Having said that, let me finish here. Again, I'm going to remind you that at 1:40, at 13:40, I have an office hour. I'll be waiting there. So if you want to ask any questions, then you can come there. Okay. Just keep this in mind.